Hello all. We are here for week 5. I'm going to start with set 15. We will see how wordy I am. And if I take too long, I will just do set 15. If I don't take too long, I will go on to set 16. I'm kind of in a time crunch here. I've got a meeting coming up. So start with set 15, see how long it goes. It's probably just going to be set 15 because I talk too much. All right, so set 15, we're moving into rotational kinematics, torque, rotation, centripetal acceleration. I know a lot of you are mechanical engineering students. This is right up your alley. Torque is fun stuff, huh? Okay, so see what I mean? I just can't keep my mouth shut. All right, let's start with number 2 in chapter 7. Yes. Number 2 says a bicycle tire is spinning clockwise at 2.5 radians per second during a time period of delta t equals 1.25 seconds. The tire is stopped and spun in the opposite counterclockwise direction, also at 2.50 radians per second. Calculate A, the change in the tire's angular velocity, and the tire's average angular acceleration. Some of these words are difficult for me to say, I guess. Okay, so if we look at what professor asked us to do, first he says, additionally plot WT assuming, or not W, that's not W, sorry, omega, omega t assuming constant angular acceleration and calculate angular displacement during this time from the graph. So let's start with that. It might help you see things a little bit more clearly for this problem. And if you see what I posted, I did it afterwards, but here I'm going to do it before. So let's do omega and t. And we end at 1.25. Let's see, 0.25, 0.5, 0.75, 1, 1.25. Suck at this. All right. And we have 2.5. So let's do 0.5, 1, 1.5, 2, 2.5. And then we spin it the other way. So let's do 0.5, negative 0.5, negative 1, negative 1.5, negative 2, negative 2.5. Okay. All right, so we're assuming constant angular acceleration. And we are starting with 2.5 radians per second. So we are going to start here. And if we have a constant angular acceleration, we are going to so how can I word this? So if we have our tire spinning like this, and well, I guess in the video it would be like this. If we stop it, so we stop like this, that wouldn't be constant, but if we stop it like this, that would be a constant acceleration. Note this would be a negative acceleration. So on our graph, we're going to see a downward. And then we're going to spin it in the opposite direction. So we could have, we could pick which one we want for negative and positive. It makes more sense if we're stopping to have a negative acceleration. So deceleration equals negative. But you could pick clockwise as being negative and counterclockwise as being positive. It's really up to you. I think the graph makes more sense to do it the way that I'm going to do it, just visually. So we've got spinning clockwise as positive. We're going to stop it, and then it's going to speed up again. to 2.5. If we have a constant acceleration, that means that right in the center of our time is where we are going to have our stopped. Sorry, I just read to make sure that I understood this and I didn't do the problem wrong. So in the center of the 1.25 seconds is where we're going to have our graph at 0. So I'm going to go ahead and mark that here. That's going to be like right here. It is 0.625 is going to be in the center of 1.25. So we are going to end here. We're going to begin here. I don't really have a straight edge, so we're going to do like this. Okay. So our professor has asked us to make this graph. So we've made this graph and to calculate angular displacement during this time in the graph. So how do we find angular displacement? So angular displacement is analogous to displacement on our V over T graph. And we find displacement with calculating the area under the graph. So what we would do is we would calculate and we would calculate, I don't do that. We would calculate and just visually, we can see that those look about even. And what we can see is that one is above the graph and one is below the graph. And so we're going to get 0 because they're going to negate each other. So what we're going to have is we're going to have top is going to be 2.5 times 0.625. That's right. I can't believe I don't know what 0.25 divided by 2 is. That's right, 0.625. Jeez. We're going to have 1.5625. And then below the graph, we're going to have negative 2.5 times 0.625. So we're going to negative. And we're going to add these two together and we're going to get 0. So our angular displacement is 0, which makes sense if we think about the tire spinning. So let's say our tire is here. Let's say our tire spins. Let's put a little mark on our tire here. Let's say we spin our tire and the mark goes right here. If we stop our tire when the mark is right here, and then we spin our tire back, if we are spinning our tire back the same, with the same angular, with the same, at the same time period, with the same angular acceleration, you're going to see that it's going to come, it's going to start here and it's going to come right back here. So you're going to not have moved. So this makes sense. All right, so let's solve the actual problem that the book wants us to solve. And that is A. So we're going to do what we always do. We're going to write down what we need. We're going to write down what we know. If you have gone online and looked, I have posted another I don't know, cheat sheet or notebook paper, yellow paper, whatever you want to call it. Yellow paper, probably nobody calls it. Oh gosh, I'm so old. I have gone and posted this, and it is basically just taking our linear kinematic equations or our translational kinematic equations and put them into our rotational kinematic equations, kind of showing the connection between the two. And whenever you're doing homework, you can just pull that up and have that available. And then it's very easy to see, okay, what do I have? What do I not have? What do I need? And figure out what equations that you need. Figure out what equations that you can use. Okay, so A is asking us for delta omega. We are given omega I is 2.50. We are given delta F is negative 2.50. We are given T equals 1.25 seconds. All right, so delta omega, we don't even have to look at our kinematic equations because delta omega is just what is the change in our omegas. And so really you just subtract one from the other. So let's take delta omega. We're going to do 2.5, 2.50 radians per second minus, now remember we have a negative 2.50, so we're going to put that in brackets here. These two are going to cancel out. We're going to get a positive. So we're going to end with 5.00 radians per second. So our delta omega is 5.00 radians per second. B asks us, I lost it here. Oh, I clicked off of it. Sorry. The tire's average angular acceleration. Okay. So now we're going to look at our kinematic equations. Pull them up again. See whichever one's the easiest. I'm going to choose to use this one. Omega I equals, plus. I'm going to rearrange to solve, Always write down what you need so you know what you're solving for. Rearrange to solve for alpha. We get this. And we end up with, plug everything into our calculator, we get 4.00 radians per second. All right, and a lot of these problems, none of these problems I get answers for. Some of them, the book actually gives the answers, kind of like the back of the book. They just give you the numbers, and so I can check my work. Some of them don't. If you ever see that I've made a mistake or I've done something really stupid, because I make stupid mistakes a lot, just dumb math errors, like I multiply instead of subtract or whatever, call me out on that. I'm not above reproach. I make really dumb mistakes all the time, like 3 + 2 = 6. Swear to God. A couple semesters ago in class, I divided by 0. Good Lord. Looked out at the class and half the class was mad at me. Good heavens. All right, number 6, moving right along. Again, got me coming up. I need to keep moving. Centrifuge, this is fun. in a medical laboratory rotates at an angular velocity of 3,600 revolutions per minute. When switched off, it rotates through 50.0 revolutions before coming to rest. Find the constant angular accelerations in radians per second squared of the centrifuge. We're going to always try to find our answers in radian, or not radians per second, sorry. Our answers in SI units, unless we are working in a field where we don't use SI units. As a physicist, most of the time we're going to use SI units in, if you go into an engineering field, unless you work outside of the country, there's a good chance you're not going to use SI units. This is a physics class, and it is not a condensed matter physics class. Many times we use, in condensed matter, we don't use SI units. Just assume that you're going to have to use SI units here. So it doesn't really have to say in radians per second. Just know that you're going to have to convert that. Okay, so what are we looking for? Angular acceleration. What do we know? We know omega, 3,600 revolutions per minute. We're just going to go ahead right away and convert that. We know that one revolution is going to be 2 pi radians. Why? Because it's a circle. One circle is 2 pi radians, and one revolution is one trip around that circle. And we know that 1 minute is going to give us 60 seconds. This is going to give us 120 pi radians per second. Leave everything in pi radians. In this class, I think they have you put things in the end. They have you figure things out with your calculator in decimal and, you know, use your significant digits. In upper level classes, it's very common to just leave it in pi radians. So leave everything in pi, and then a lot of times pi's cancel out, especially when you get in like huge equations, you have all these pi's all over. Leave things in pi until you get to the very end. All right, so what else do we know? We know that our omega, this is our omega F. No, this is our omega I. Our omega F equals 0. Oh, ouch. It's going to be 0 revolutions per minute, but 0 is also going to be radians per second. So we're just going to put radians per second here. All right. And we know that our delta theta is going to be 50.0 revolutions. And we know that one revolution is going to give us 2 pi radians. So we're going to have 100 pi radians. All right, so we're going to go back to our kinematic equations. We're going to figure out whichever looks easiest to us. I'm going to go ahead and use this one. I'm going to solve for, I'm going to rearrange for alpha. And plugging in what we know, using our calculators, we get 226 radians per second squared. Okay, there's the B to this one, right? Oh, there's not. Okay, that's the answer. Oh, there is a B. Professor asked us to also calculate the amount of time it takes for the centrifuge to come to rest. So this is our A. Okay. Our B is going to be T equals. And again, we're going to look at our kinematics equations. This one I think is probably the simplest, which we used in the equation above. We're going to rearrange and solve for T, and we're going to get omega F minus omega I all over alpha. Plug in our values. Use our calculator, we get 1.67 seconds. So let me do this here just to, so our omega F is 0 because it stops at rest. We got up here 120 radians. And our alpha, when we plugged in everything, this came to 72 pi radians. And then plugging in your calculator, we get this. So if we use this, put this here. These cancel out and the pi's cancel out. And then you get the 1.667. So what I was saying here is that keep everything in pies until the very end and then kind of use your calculator. It makes it much simpler. So this one was far simpler. Because the pies canceled out and then you're just dividing 120 by 72 instead of whatever 120 times pi is divided by 1.6667, whatever it is. Okay. All right. Point made. Moving on. 7. A bicycle starting at rest produces an angular acceleration of 1.6 radians per second squared. For wheels that are 38.0 centimeters in radius, what is the bicycle's linear acceleration? All right. So we are looking for A. We are looking for A. We are given alpha was 1.60 radians per second squared. And we are given R equals 0.38 meters. Whenever you can just put something in an SI unit, change it to kilograms, meters, and it's a just do it in your head and put it down. So much simpler than waiting to the end and trying to do it a whole bunch. Okay. What is the bicycle's linear acceleration? Okay, our book gives us an equation. Linear acceleration equals R times alpha. That's simple enough. We're just going to plug in values. We've got R is 0.38 meters times 1.60 radians per second squared. And if we plug that into our calculator, we end up with 0.608 meters per second squared. Right. And B asks for what is the angular speed of the wheels when the cyclist reaches 11.0 meters per second. So what is omega when V equals 11.0 meters per second? So when angular speed, angular, rotational, those are kind of words that we're looking for. Omega, alpha, angular, angles, theta. You can also look at units. So meters per second. Meters per second is going to be linear. So you can look for words like angular or linear, or translational is going to be linear, or you can look for radians per second, angular, meters per second, linear. So 11.0 meters per second, that's going to give us a V. All right, so we know that omega equals V over R. We're going to solve for omega. Very, very simple. We're just plugging in values here. What was our R value? 0.38. We get omega equals 28.9 radians per second. And C asks for how many radians have the wheels turned through in this time. All right, so what are we looking for? We are looking for delta theta. And we know that omega F is 28.9. This is what we found above. And our problem says our cyclist starts at rest. So we know that omega I equals 0 radians per second. So we're gonna look at our kinematic equations, look at what we're given, look at what we're not given, look at what we need, and we're gonna just plug stuff in. We're gonna use this equation here. The easiest. Now, looking at this equation, there are two things that you can do here, and I'm going to tell you to always, always, always do this if you can. This equation is omega F squared minus omega I squared over 2 alpha. Now, you can put omega F equals 28.9 radians per second squared, or you can put V over R. V and R were given in the problem. Omega F we found. You don't want to put in what we found because we're squaring it. So that makes our number less exact. And we're assuming that V and R are relatively exact because they're given. And this problem actually comes out wrong if you use WF that we found above. So we're going to V over R squared minus 0 squared. I love when we can put zeros in. Makes life so much easier. 2 alpha was given, correct. What is it? 1.6. And we get, once we plug everything into our calculator, equals 261. I think what happens is, I found it both ways. I think what happens if you plug in the 28.9, I think what you get is 2.60 maybe? Yeah, I'm gonna say. I know it's wrong. I know the significant digits end up giving you the wrong answer. Barely the wrong answer, but Cengage doesn't care. It's just gonna mark it wrong. All right, so D, how far has the bicycle traveled? This is D, or we would also call that delta X. So we know that one turn of our bicyclist wheel is going to be 2 pi r, which we can calculate because we're given r, and it's also going to be 2 pi radians. So our delta X is going to be delta theta over 2 pi times 2 pi r. We're going to cross these, and we're going to get theta times r. And if you plug in known values, given values, and significant digits, so we get 99.2 meters. And Merry Christmas, that was 7. Moving along to 14. Most definitely will not be going on to set 16. An electric motor rotating a workshop grinding wheel at a rate of 1.00 times 10 squared revolutions per minute is switching off. Assuming the wheel has a constant negative angular acceleration of magnitude 2.00 radian seconds squared, how long does it take for the grinding wheel to stop? Okay, so A, how long? We're looking for time. So T, we are given omega I equals 1.00 times 10 revolutions per minute. We're going to go ahead and just do that right away. 1 revolution is going to be 2 pi radians. 1 minute is going to be 60 seconds. And we get 3.33333333 pi radians per second. We are also given angular acceleration of 2.00 radians per second squared. I've been a little, I don't know, fast and loose with this. I think it's decelerating, so we're going to call it negative. You'll see in my work that I've not been very good with that. It's decelerating, it's negative. We're going to say, we also know omega F, we're going to say it comes to a stop. All right, so how long does it take to come to a stop? We're going to, again, look at our kinematic equations, figure out what's the easiest. Anytime we can plug in zeros, that's going to be the easiest. We're going to rearrange to solve for t. We're going to get omega F minus I over alpha, plug in known values, over -2, and we get 5.24 seconds. Okay. B says, how many radians has the wheel turned during this interval found in A? Okay, so now when we read the question, usually I tell you to go back and look at your kinematic equations and try to use kinematic equations that only have variables that we were given. And we actually can do this. However, this problem specifically says, how many radians has the wheel turned during the interval that you find? So it's saying use the time that you found and find this value. So we're going to use one that specifically has time in it. And we are looking for delta theta. We're going to use this one, omega F plus omega I P, which is basically just finding the average. We're going to, again, plug in values. Divided by 2 times the time. And we end up with delta theta equals 27.4 radians. All right, so that was set 15. I have 30 seconds left before 6:30. I will not be going on to set 16, but you can expect that to be posted tomorrow. Thank you all.